right now, as you sit there watching this, every single credit card in your wallet, every hard drive on this planet, every magnetic strip on every hotel key in every city on Earth could be wiped clean, all at once, by an object no bigger than a city, not a weapon, not a bomb, a dead star. And it wouldn't even have to be close. If a magnetar drifted to just half the distance between the Earth and the Moon, roughly 190,000 kilometers away, its magnetic field would reach out across that void, invisible and silent, and erase every piece of magnetically stored information on the planet. Your bank cards, your identity, gone. But that's the gentle version. Get within about 1,000 kilometers of one, and the magnetic field would rearrange the electron clouds of every atom in your body. Not metaphorically. Literally, the chemistry holding you together would stop working. You wouldn't explode or burn. You'd simply cease to be a biological organism. The bonds that make you would fail. This is a magnetar, and the universe has scattered them across our galaxy like landmines buried in a dark field. But magnetars don't just sit there being terrifyingly magnetic. They crack, they shatter, they experience earthquakes so violent that on a seismological scale, they would register as a magnitude 23. Roughly 100 trillion times more powerful than the worst earthquake ever recorded on Earth. When this happens, the magnetar screams. It sends out a wave of gamma rays and X-rays so powerful that it can ionize the upper atmosphere of our planet from 50,000 light years away. That's halfway across the entire Milky Way, and it happened. On December 27th, 2004, one of these starquakes shook a magnetar called SGR 18-6-20, and the radiation from that event traveled for tens of thousands of years before it slammed into Earth, blinding satellites and disrupting the ionosphere. In a fraction of a second, this dead star, this burned-out husk no wider than Manhattan, released more energy than our sun puts out in 250,000 years. And here's the part that might keep you up at night. New research published in 2025 suggests that when magnetars crack open like this, they don't just release energy. They forge gold, platinum, uranium, the precious metals in your phone, in your jewelry, in the fillings of your teeth. Some of that material may have been born in the catastrophic fracture of a dead star's crust, billions of years before the Earth even existed. This is the story of nature pushed to its absolute limits, of stars so dense that a teaspoon of their material weighs more than every car in America combined, of magnetic fields so strong they warp the vacuum of space itself, of worlds that orbit the corpses of exploded suns, bathed in radiation, haunted by the ghosts of systems that died long ago, of nuclear pasta buried deep within stellar crusts, of superfluids spinning in quantized vortices at millions of degrees. Millisecond radio flashes that cross billions of light years to reach our telescopes, carrying information about the most violent magnetic events in the cosmos. This is the story of magnetars, starquakes, glitches, and zombie worlds. And if you're wondering how all of these things connect, the answer is beautifully simple. They are all consequences of one event: the death of a massive star. Everything we are about to explore, every shattered crust and forged atom and haunted planet, traces its origin to a moment of cosmic catastrophe. A star collapsing under its own weight. What happens in the seconds, years, and billions of years after that collapse produces the most extreme physics in the known universe. And we're going to start at the end. Because to understand the most extreme objects in the universe, you first have to understand what it means for a star to die. Somewhere in the Milky Way, right now, a massive star is dying. It has been alive for perhaps 10 million years, which by cosmic standards is barely a blink. Our sun, for comparison, is already about 4.5 billion years old and has another 5 billion to go. But massive stars live fast and die young. The bigger they are, the harder they burn, and the faster they exhaust their fuel. Throughout its life, this star has been a furnace of nuclear fusion. In its core, hydrogen atoms have been slamming together under unimaginable pressure and temperature, fusing into helium and releasing energy in the process. That energy pushes outward against the crushing weight of gravity, pulling inward. For millions of years, these two forces have been locked in a delicate balance, and the star has been stable, burning brightly, a beacon in the galactic neighborhood. But hydrogen doesn't last forever. When the hydrogen runs out, the core contracts under its own gravity, and the temperature shoots up. Now, the star begins fusing helium into carbon and oxygen. When the helium runs out, the cycle repeats. Carbon fuses into neon, neon into oxygen, oxygen into silicon. Each stage is shorter than the last. Each stage burns hotter. The star develops an onion-like structure with layers of progressively heavier elements nested inside each other like Russian dolls. And then, deep in the core, silicon begins fusing into iron. And this is where the music stops. Iron is the dead end of nuclear fusion. Every element lighter than iron releases energy when it fuses. Every element heavier than iron requires energy to fuse. Iron is the break-even point, the element that sits at the bottom of the nuclear binding energy curve. When the core fills with iron, no more energy can be extracted from fusion. The outward push of radiation pressure suddenly vanishes. What happens next takes less than a second, and it is one of the most violent events in all of physics. The iron core, now roughly the mass of our sun, but only about the size of Earth, collapses under its own gravity at speeds approaching a quarter of the speed of light. In just a few tenths of a second, the core shrinks from a volume roughly the size of our planet to a ball just 20 or 30 kilometers across. The collapse is so violent and so fast that the outer layers of the star, which are still happily fusing lighter elements, don't even know what's happened yet. They're still hanging there in space, supported by nothing, because the core that held them up has just vanished out from under them. It's as if you pulled the foundation out from under a skyscraper. The floors above haven't had time to notice. For a brief, surreal moment, the star's outer envelope is just hovering, supported by its own inertia, while beneath it, the core has already compressed to nuclear density. As the core collapses, temperatures soar to over 100 billion degrees. The density becomes so extreme that protons and electrons are forced to merge, creating neutrons and releasing a flood of ghostly particles called neutrinos. This is called neutronization, and it converts the collapsing core from a ball of iron atoms into a ball of almost pure neutrons. Then the core hits a wall. At nuclear density, roughly 230 million tons per cubic centimeter, the neutrons resist further compression. The strong nuclear force, the same force that holds atomic nuclei together, pushes back. The collapsing core bounces. That bounce sends a shockwave screaming outward through the infalling material. At the same time, the torrent of neutrinos, carrying roughly 99% of the total energy released, slams into the surrounding layers. In the span of a few hours, the combination of the shockwave and neutrino energy rips the star apart in a supernova explosion, one of the most energetic events in the known universe. For a few weeks, this single dying star can outshine its entire host galaxy, a blaze of light visible across billions of light years. But the core remains, squeezed to an almost incomprehensible density, spinning rapidly, seething with residual heat, a ball of neutrons roughly 20 kilometers across, but containing more mass than the Sun. This is a neutron star. The numbers that describe a neutron star sound less like physics and more like a fever dream. A single teaspoon of neutron star material, scooped from its surface and brought to Earth, would weigh roughly 1 billion tons. That's approximately the combined weight of every human being on the planet, compressed into a volume smaller than a sugar cube. The surface gravity is about 200 billion times stronger than Earth's. If you dropped a marshmallow onto a neutron star from a height of 1 meter, it would hit the surface with the energy of a small nuclear weapon. The escape velocity, the speed needed to leave the surface, is about 1/3 the speed of light, and the neutron star spins. Conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in, means that the slow rotation of the original star is amplified enormously when it collapses. A star that rotates once every few weeks can become a neutron star that rotates hundreds of times per second. These rapidly spinning neutron stars are called pulsars because they emit beams of electromagnetic radiation from their magnetic poles. As the star spins, these beams sweep across space like the beam of a lighthouse. And if one of them happens to point toward Earth, we detect a regular pulse of radio waves. The regularity of these pulses is so precise that when Jocelyn Bell Burnell first detected them in 1967, her advisors half-seriously labeled them LGM-1 for little green men, considering the possibility that they might be signals from an extraterrestrial civilization. They weren't, of course. They were something more impressive: the spinning remnants of dead stars, broadcasting their existence to anyone with a radio telescope pointed in the right direction. Pulsars were quickly recognized as one of the most useful tools in astrophysics. Their pulse timing is so precise that any disturbance to the neutron star, whether caused by an orbiting companion, a passing gravitational wave, or a disturbance in the star's interior, shows up as a measurable change in the arrival times of the pulses. This makes pulsars extraordinarily sensitive probes of their environments. They have been used to confirm the existence of gravitational waves, to measure the masses of companion stars with exquisite accuracy, and, as we'll see later, to discover the first planets ever found outside our solar system. But not all neutron stars are created equal. Some of them are born with something extra, something that elevates them from merely extreme to genuinely terrifying. Some of them are born as magnetars. The interior of a neutron star is one of the least understood places in the entire universe. We've never been there. We can't recreate its conditions in any laboratory on Earth. The densities involved exceed what can be achieved in particle accelerators by orders of magnitude. And yet, through a combination of theoretical physics, computer simulations, and clever observations, scientists have built a surprisingly detailed picture of what lies beneath the surface of these dead stars. And it is, quite frankly, one of the strangest places imaginable. Start at the surface. The outermost layer of a neutron star is a thin ocean of plasma, perhaps only a few centimeters deep, composed of hydrogen and helium at temperatures of millions of degrees. Below that lies a solid crust, roughly 1 to 2 kilometers thick, made of iron nuclei arranged in a crystalline lattice, surrounded by a sea of free electrons. This crust is extraordinarily strong. In fact, it is the strongest known material in the universe, billions of times stronger than steel. And yet, as we'll see, it can still break. As you descend through the crust, the pressure increases relentlessly. The iron nuclei at the surface give way to progressively more exotic and neutron-rich nuclei, elements so unstable that they could never exist on Earth. At a depth where the density reaches about 400 billion grams per cubic centimeter, something remarkable happens. The nuclei become so bloated with neutrons that they can no longer hold them. Neutrons begin to drip out of the nuclei and flow freely through the lattice. This is called the neutron drip point, and it marks the boundary between the outer crust and the inner crust. Below the neutron drip point, things get truly bizarre. The competition between the attractive nuclear force, which tries to pull protons and neutrons together, and the repulsive electromagnetic force, which tries to push protons apart, creates structures of incredible complexity. The nuclei, no longer spherical, deform and merge into exotic shapes. Some form long cylindrical rods. Others flatten into broad, thin sheets. Still others create tunnel-like cavities threaded through a matrix of nuclear material. Physicists have given these structures evocative names borrowed from Italian cuisine: gnocchi, spaghetti, lasagna, bucatini, and Swiss cheese. Collectively, they're known as nuclear pasta. Nuclear pasta is not just a curiosity. It may be the strongest material in the universe, even stronger than the crystalline crust above it. Computer simulations suggest that deforming nuclear pasta would require roughly 10 billion times more energy than deforming steel. And this pasta layer, sitting at the base of the crust, acts as a critical interface between the rigid outer shell and the fluid interior of the star. It influences how heat escapes the star, how the magnetic field evolves, and how the star responds to stress. Understanding nuclear pasta is essential to understanding everything else about neutron stars, from their cooling rates to their starquakes. There is something almost poetic about the fact that the most extreme material in the universe bears such a mundane name. Physicists named the shapes after what they looked like in simulations. Gnocchi for the spherical blobs, spaghetti for the cylindrical rods, lasagna for the flat sheets, bucatini for the hollow tubes, and Swiss cheese for the phase where spherical voids are punched through an otherwise continuous nuclear medium. As you descend through the inner crust, increasing in density, the shapes progress through this sequence. Gnocchi gives way to spaghetti, spaghetti to lasagna, and then the pattern reverses as you approach the core. The lasagna develops holes that become bucatini, which opens up further into Swiss cheese. And then, finally, the nuclear structure dissolves entirely into the uniform fluid of the outer core. Remarkably, these same shapes appear in a completely different context, inside living cells. The endoplasmic reticulum, a membrane structure inside eukaryotic cells, forms strikingly similar spaghetti-like tubes and lasagna-like sheets. The physics is entirely different. Molecular forces in water versus nuclear forces at 100 trillion times the density. But the underlying mathematics of energy minimization produces the same geometric solutions. Nature, it seems, has a limited imagination when it comes to shapes. And nuclear pasta is the universe's proof that the same principles of geometry apply everywhere, from the tiniest organelle to the densest star. Recent observational evidence supports the existence of nuclear pasta. In 2013, Jose Pons and collaborators showed that the spin periods of isolated pulsars cluster below a maximum value that can be explained if the base of the crust contains a highly disordered material, exactly what nuclear pasta would look like. This was the first indirect observational evidence for the reality of nuclear pasta, and it has since been bolstered by additional studies of neutron star cooling and magnetic field evolution. Below the pasta layer, you enter the outer core, and here the physics shifts dramatically. The density is now so extreme, several times the density of an atomic nucleus, that individual nuclei have completely dissolved. What remains is a soup of neutrons, with a small admixture of protons and electrons. And here's the astonishing part. At these densities and the temperatures found in older neutron stars, the neutrons form a superfluid. A superfluid is a state of matter that flows with absolutely zero viscosity, zero friction. On Earth, superfluidity has only been achieved in laboratory conditions at temperatures within a few degrees of absolute zero, using liquid helium cooled to extreme lows. Inside a neutron star, superfluidity occurs at temperatures of hundreds of millions of degrees, because the enormous density allows neutron pairs to form at much higher energies than would otherwise be possible. This neutron superfluid has no resistance to flow. It can rotate indefinitely without slowing down, and it behaves in ways that have profound consequences for the observable behavior of the star. The protons in the outer core, meanwhile, form a superconductor, a state where electrical currents flow without resistance. This superconducting proton fluid is what maintains the neutron star's magnetic field over thousands of years, trapping and sustaining the field lines that thread through the star. Deeper still, in the inner core, the physics becomes genuinely uncertain. The density here may exceed 10 times the density of normal nuclear matter, and nobody is entirely sure what happens to neutrons and protons under those conditions. Some theories suggest that the neutrons and protons break apart into their constituent quarks, forming a quark-gluon plasma, a state of matter that hasn't existed freely in the universe since the first microseconds after the Big Bang. Other models propose the appearance of exotic particles called hyperons, or the formation of a condensate of particles called kaons? We simply don't know. And that uncertainty is one of the reasons neutron stars are so valuable to physicists. They are laboratories for the most extreme conditions in nature, places where the known laws of physics are pushed to their breaking points. This is the world inside a neutron star. A crystalline iron surface, a layer of nuclear pasta, a superfluid core wrapped around an unknowable center. And threaded through all of it, a magnetic field that can range from 1 trillion times stronger than Earth's to something far, far beyond that, because some neutron stars are born with magnetic fields so strong that they redefine what it means to be extreme. Some of them are born as magnetars. For most of the 20th century, neutron stars were understood primarily as pulsars, spinning remnants that broadcast radio beams into the void with clockwork precision. Their magnetic fields, while formidable by earthly standards, roughly 1 trillion Gauss compared to Earth's half a Gauss, were considered a well-understood feature of their formation. The collapse of the parent star's core concentrated whatever magnetic field the star originally possessed into a much smaller volume, amplifying it enormously. Conservation of magnetic flux, the same principle that makes a bar magnet stronger when you squeeze it into a smaller shape, seemed to explain everything. But in 1979, something happened that didn't fit the existing picture. On March 5th of that year, a wave of gamma rays washed over the solar system, tripping detectors on multiple spacecraft scattered across the inner solar system. The Venera probes near Venus, the Pioneer Venus orbiter, the ISC Eminus 3 satellite near Earth, and several other instruments all recorded a sudden, intense flash of high-energy radiation. The burst was unlike anything seen before. It began with a tremendously bright initial spike, lasting only about 0.2 of a second, but containing as much energy as the sun radiates in 1,000 years. This was followed by a pulsating tail of softer radiation that lasted for about 100 seconds, with the pulsations repeating every 8 seconds. By triangulating the arrival times of the burst at different spacecraft, astronomers were able to pinpoint the source to a small region of the sky. It lay in the direction of the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way about 160,000 light-years away. More specifically, it appeared to come from the vicinity of a supernova remnant, the expanding shell of gas left behind by a star that had exploded roughly 3,000 years earlier. The energy involved was staggering, far beyond what the known mechanisms of pulsar physics could explain. If the source really was in the Large Magellanic Cloud, then the initial spike alone had released more energy in 0.2 of a second than most stars emit in their entire lifetime. The event was catalogued as GRB 790,305 billion, puzzled over and largely set aside. Over the next several years, 2 more similar sources were found, objects that occasionally flashed soft gamma rays from the same locations in the sky. They were called soft gamma repeaters, or SGRS, because they seemed to repeat. But nobody could explain what they were. It would be more than a decade before anyone could explain them. The explanation came from 2 young physicists, Robert Duncan and Christopher Thompson, who in 1987 began a series of calculations that would change our understanding of neutron stars forever. Working initially at Princeton, Duncan and Thomson were trying to understand why pulsars had such strong magnetic fields. But as they worked through the physics, they realized something startling. Under certain conditions, the magnetic field of a neutron star could be amplified far beyond what simple conservation of flux would predict. The key was what happens in the first few seconds after the neutron star forms. At birth, a neutron star is unimaginably hot, hundreds of billions of degrees, and its interior is turbulent. Convective currents of neutron-rich fluid churn violently, driven by the intense heat and the enormous differences in temperature between the core and the surface. If the neutron star is also spinning rapidly, which many of them are, this combination of rapid rotation and violent convection can drive a process called a magnetohydrodynamic dynamo. A dynamo is essentially a self-reinforcing feedback loop. Moving an electrically conductive fluid generates electric currents. Those currents generate magnetic fields. Those magnetic fields, in turn, influence the flow of the fluid, which generates stronger currents, which generate stronger fields. On Earth, this is the process that maintains our planet's magnetic field, driven by the slow convection of molten iron in the outer core. In the Sun, a similar dynamo drives the solar magnetic cycle. But in a newborn neutron star, the conditions for dynamo action are turned up to an almost absurd degree. The fluid is far denser, far hotter, and far more conductive than anything on Earth or in the Sun. The rotation rates are vastly higher, and the convection is far more violent. Duncan and Thomson calculated that under these conditions, the dynamo could amplify the magnetic field to values of 10 to the 15th Gauss, 1,000 times stronger than a typical pulsar, in a matter of seconds. They called these hypothetical ultramagnetic neutron stars magnetars. The name, a blend of magnetic and star, appeared in print for the first time in their landmark 1992 paper. In that paper, they also proposed that magnetars were the explanation for the mysterious soft gamma repeaters, or SGRs, those enigmatic objects that had been sporadically flashing gamma rays since the 1979 event. The idea was bold and, at the time, widely skeptical to the broader astronomical community. When Duncan and Thomson first presented their theory at a conference in 1992, they were given just 3 minutes to make their case, but they were right. Over the following decade, observations piled up in support of the magnetar hypothesis. The clincher came in 1998, when Krissa Kuvaliatu and her collaborators at NASA's Marshall Space Flight Center used the Compton Gamma Ray Observatory to study another soft gamma repeater, SGR 190+14. They measured its spin, and critically, its rate of spin down, the rate at which the star was losing rotational energy. The spin down rate was enormous, consistent with a magnetic field far stronger than any ordinary pulsar. Then, on August 27th of that year, SGR 190+14 unleashed a giant flare so powerful that it overwhelmed gamma ray detectors across the solar system. The evidence was becoming overwhelming. By the early 2000s, the magnetar hypothesis had been extended to explain another class of mysterious neutron stars, called anomalous X-ray pulsars, or AXPS, which emitted far more X-ray energy than their rotation could account for. Duncan and Thompson's theory showed that both SGRS and AXPS were magnetars, powered not by rotation like ordinary pulsars, but by the slow decay of their colossal magnetic fields. Today, astronomers have confirmed around 30 magnetars in the Milky Way and the Magellanic Clouds. They believe that roughly 10% of all neutron stars may be born as magnetars, meaning that the galaxy could harbor as many as 30 million dead magnetars, whose fields have decayed below detectable levels. They are rare, but they are not unique. They are a natural product of stellar death, born in the fires of supernovae, and they are, without question, the most magnetically powerful objects in the known universe. What distinguishes a magnetar from an ordinary pulsar is not just the strength of its magnetic field, but the way that field shapes the star's behavior. Ordinary pulsars are powered by rotation. Their energy comes from spinning, and as they radiate energy, they slow down. Magnetars are powered by magnetism. The slow decay of their colossal magnetic field heats the interior of the star, drives electric currents through the crust, and triggers the violent bursts of X-rays and gamma rays that are the magnetar's signature. This is why magnetars can remain brilliant X-ray sources even when they are spinning too slowly to generate significant rotational energy. But a magnetar's magnetic life is brief by cosmic standards. The intense fields decay after about 10,000 years, dissipating their energy as heat and radiation. After that, the magnetar fades into quiescence, becoming an unremarkable neutron star, its glory days behind it. The magnetars we observe today are all relatively young, born within the last 10,000 years or so from supernova explosions of massive stars. They are the cosmic equivalent of embers, still glowing fiercely from the fire that created them, but slowly cooling toward darkness. In 2019, a German-British research team used large-scale computer simulations to demonstrate another pathway for magnetar formation. They showed that the merger of two massive stars could generate the strong magnetic fields needed to produce a magnetar, offering an alternative to the conventional picture of a single massive star collapsing in a supernova. The simulations focused on Tau Scorpii, a magnetic star about 500 light-years from Earth that is believed to be a blue straggler, the product of a stellar merger. The team found that the turbulence generated during the merger process could amplify magnetic fields to levels consistent with magnetar strength fields, suggesting that roughly 10% of massive stars, those that have undergone mergers, could produce magnetars when they eventually die. And then, just recently, in nearly 2025, astronomers reported that they had likely witnessed the birth of a magnetar for the first time, analyzing an unusually bright supernova designated SN 2024 AFAV. A team including Alexei Filipenko of the University of California, Berkeley, detected strange wobbles in the supernova's light curve that they attributed to a rapidly spinning magnetar at the center of the explosion. They estimated that the newborn magnetar was spinning roughly 238 times per second and had a magnetic field about 300 trillion times stronger than Earth's. It was the first direct evidence of a magnetar being born, a cosmic birth announcement delivered in the language of gamma rays and distorted light. To say that a magnetar has a strong magnetic field is an almost comical understatement. It's like saying the ocean is somewhat damp. The magnetic field of a typical magnetar, measured at its surface, ranges from about 100 billion to a quadrillion Gauss. For context, the strongest continuous magnetic field ever produced in a laboratory on Earth is roughly 450,000 Gauss. The strongest pulsed magnetic field, achieved only for tiny fractions of a second, reaches about 25 million Gauss. A magnetar exceeds both of these by factors of millions to billions. At these field strengths, physics itself begins to behave differently. The vacuum of space, which we normally think of as empty nothingness, is actually a seething cauldron of virtual particles popping in and out of existence on timescales too brief to measure directly. This is a consequence of the Heisenberg uncertainty principle, which allows particles to borrow energy from the vacuum for extremely short durations. Under normal conditions, these virtual particles have no observable effect. They appear and vanish in balanced pairs, leaving no trace of their existence. But in the presence of a magnetar's field, everything changes. The vacuum becomes polarized. The magnetic field is so strong that it aligns the virtual electron-positron pairs that constantly flicker in and out of existence, creating a preferential direction in what should be directionless empty space. The vacuum behaves like a crystal, splitting light into two differently polarized beams, a phenomenon called vacuum birefringence. This effect was predicted by the quantum theory of electrodynamics, or QED, in the 1930s by Werner Heisenberg and Hans Heinrich Euler. But it was extraordinarily difficult to test in a laboratory because the effect is vanishingly small at the field strengths achievable on Earth. In 2017, observations of a neutron star called RX Joan 1000, 856.5-3754, provided the first observational evidence that this effect is real. The vacuum of space, in the presence of a strong enough magnetic field, literally becomes a prism. Light no longer propagates the same way in all directions. The very emptiness of space is altered at even higher field strengths, approaching those of the most powerful magnetars. The quantum electrodynamic effects become even more dramatic. X-ray photons can spontaneously split into two lower energy photons, a process called photon splitting that is forbidden in normal vacuum, but becomes possible when the magnetic field provides the necessary energy and momentum. Conversely, two photons can merge into a single, higher energy photon. The normal rules of electromagnetic propagation, the rules that govern how light travels through space, are fundamentally altered. If you could somehow observe the space near a magnetar with superhuman vision, you wouldn't see the familiar clear vacuum of interstellar space. You would see a shimmering, distorted lens, a region where light itself bends, splits, and recombines in ways that have no parallel anywhere else in the universe. But the effects on empty space are just the beginning. The magnetar's field also profoundly alters the behavior of matter itself. At field strengths around 100 million Gauss, the electron orbitals of atoms are deformed. Normally, electrons orbit atomic nuclei in roughly spherical clouds. In a magnetar's field, these clouds are squeezed into elongated, needle-like shapes aligned with the field direction. Hydrogen atoms, which are normally about 1 angstrom across, become 200 times thinner. These distorted atoms can bond with each other lengthwise, forming long polymer-like chains that drape across the magnetar's surface. Get closer, and the effects become lethal. At a distance of about 1,000 kilometers, the magnetic field is strong enough to disrupt the electron clouds of every atom in a human body. The molecular bonds that hold proteins together, that allow enzymes to function, that make DNA replicate, all of these would be torn apart. Not by heat, not by radiation, by magnetism alone. Your water molecules would be distorted. Your hemoglobin would be racked into non-functional shapes. Death wouldn't be violent in any conventional sense. It would be almost clinical. The chemistry that makes life possible would simply stop working. And X-ray photons, individual particles of light in the X-ray band, behave bizarrely. In a magnetar's field, they can spontaneously split into 2 lower energy photons, or 2 photons can merge into 1. The normal rules of electromagnetic propagation, the rules that govern how light travels through space, are fundamentally altered. The energy density of a magnetar's field is equally astonishing. Energy density is a measure of how much energy is stored in a given volume of space. For a magnetar with a field strength of 10 to the 10th Tesla, the energy density of the field alone exceeds the mass energy density of lead by a factor of 10,000. In other words, the magnetic field itself is, in a very real sense, heavier than solid metal. The field contains enough energy to power the magnetar's X-ray emissions for thousands of years, even as it slowly decays. But the magnetic field doesn't just sit there passively radiating energy. It interacts with the star's solid crust, and this interaction is the source of some of the most violent events in the cosmos. The field lines thread through the crust, anchored in the superconducting interior. As the field slowly evolves, driven by internal currents and the gradual decay of the magnetic energy, it exerts enormous stresses on the crust. The crust is strong, the strongest material in the universe, but it is not infinitely strong. And eventually, the stress exceeds its breaking point. When that happens, the crust fractures. The star experiences a starquake. The concept of a starquake is eerily analogous to an earthquake, but the scale is almost incomprehensibly larger. On Earth, earthquakes occur when tectonic plates, driven by the slow convection of the mantle, build up stress along a fault line until the rock can no longer hold. The fault slips, the stored energy is released as seismic waves, and the surface shakes. The largest earthquake ever recorded, the 1960 Chilean quake, registered a magnitude of 9.5 on the moment magnitude scale. On a magnetar, the driving force is not mantle convection, but the evolving magnetic field. The field lines, anchored in the superconducting core and threading through the rigid crystalline crust, twist and deform over time. This creates enormous mechanical stresses in the crust. For a while, the crust can accommodate these stresses plastically, deforming slightly without breaking, like bending a piece of copper wire. But magnetar magnetic fields are so incredibly strong that the stresses eventually become catastrophic. The crust can no longer bend. It cracks. When the crust of a magnetar fractures, the consequences are spectacular. The fracture releases the pent-up magnetic energy in a sudden, explosive burst. The magnetic field lines, suddenly freed from their anchoring in the broken crust, snap and reconfigure. A process called magnetic reconnection. This releases a fireball of electrons, positrons, and gamma-ray photons, a superheated plasma trapped in the magnetic field above the fracture site. This fireball is anchored to the surface of the star, rotating with it, and as it cools and shrinks, it emits a pulsating tail of X-rays modulated by the star's rotation period. The biggest of these events are called giant flares, and only 3 have ever been observed from magnetars in or near our galaxy. In 1979, 1998, and 2004. Of these, the 2004 events from SGR 18 6-20 were by far the most powerful. SGR 18 6-20 is a magnetar located roughly 42,000 light-years from Earth, on the far side of the Milky Way, in the direction of the constellation Sagittarius. It sits at the core of a radio nebula, surrounded by an unusual cluster of massive stars, including some of the most luminous stars in the galaxy. The magnetar itself is small, perhaps 20 kilometers across, spinning once every 7.5 seconds. On December 27, 2004, something broke inside SGR 18 6-20. The initial spike of the giant flare lasted just 0.2 of a second, but in that fraction of a heartbeat, the magnetar released energy equivalent to what our sun produces in 250,000 years. The total isotropic energy of the flare was estimated at 2 × 10⁻⁶ ergs, roughly 100 times more energetic than either of the 2 previously observed giant flares. The initial gamma-ray spike was so intense that it saturated every gamma-ray detector in orbit. Instruments designed to observe the most powerful explosions in the universe were completely overwhelmed, blinded by the sheer brightness. Several satellites that were not designed to observe gamma rays at all detected the event. The particle detectors on ESA's cluster and double star missions, which were designed to study Earth's magnetosphere, recorded the entire blast without being blinded, providing some of the most detailed data available. Analysis of their observations revealed that the fracture in the magnetar's crust was approximately 5 kilometers across, a significant portion of a star only a few tens of kilometers in diameter. The radiation from the flare washed over Earth and partially ionized the upper atmosphere, briefly increasing the ionization of the ionosphere. This was detected by ground-based instruments. The flare was even detected by its reflection off the surface of the moon. For a fraction of a second, this dead star, 50,000 light-years away, was brighter than any source outside the solar system. To put the danger of this event in stark perspective, scientists have calculated that a similar blast within about 3 parsecs, or roughly 10 light-years, of Earth would severely damage the ozone layer and trigger a mass extinction event. The effects would be comparable to a 12-kiloton nuclear blast at an altitude of 7.5 kilometers. To give you a sense of what that means, 12 kilotons was roughly the yield of the bomb dropped on Hiroshima but detonated in the upper atmosphere, affecting the entire planet simultaneously rather than a single city. The flare also produced an expanding radio nebula, detected in the days and weeks following the event, expanding at roughly a quarter of the speed of light. This nebula was evidence that the flare had ejected material into space, and the energy required to create it was estimated at a minimum of 4 times 10 to the 43rd ergs in the form of magnetic fields and relativistic particles. For scale, that's more energy than our sun has emitted in the last 10,000 years, released in a single event by a star no wider than a city. After the initial spike, a tail of pulsating X-rays persisted for more than 6 minutes, modulated at the 7.5-second rotation period of the magnetar. Scientists interpreted this as the slow cooling and evaporation of the trapped fireball, rotating with the star like a lighthouse beacon, gradually shrinking back down to the surface. The fireball was composed of electron-positron pairs and gamma-ray photons, trapped in the magnetic field above the fracture site, slowly annihilating as it cooled. But there was something else in the data, something that wouldn't be understood for another 20 years. A second, fainter signal, peaking about 10 minutes after the initial flare. At the time, it was noted and filed away, an unexplained afterglow. But as we'll see later, that signal turned out to be something remarkable: the radioactive glow of freshly forged heavy elements, gold and platinum being minted in real time by the violence of a cracking star. If this event had occurred within about 10 light-years of Earth, it would have been catastrophic. The radiation would have destroyed the ozone layer and triggered mass extinction. Similar in effect to a 12-kiloton nuclear weapon detonated at an altitude of about 7.5 kilometers. Fortunately, the nearest known magnetar, called 1E1000, and 48.1-5937, is roughly 9,000 light-years away, far too distant to pose any direct threat to life on Earth. On a seismological scale, if you could somehow translate a magnetar starquake into the language of Earth's moment magnitude scale, it would register as approximately a magnitude 23. The strongest earthquake in Earth's history, by contrast, was a 9.5. A magnitude of 23 is roughly a trillion times more powerful. Stars can crack, and when they do, the universe notices. But starquakes are not the only way that neutron stars reveal the secrets of their interiors. There is another phenomenon, subtler but equally profound, that has been puzzling astronomers for more than half a century. It is called a glitch. A pulsar, as we discussed, is a rapidly spinning neutron star that emits beams of radiation from its magnetic poles. Because these beams sweep across Earth with each rotation, we observe a regular pulse of radio waves, and the timing of these pulses is extraordinarily precise. Pulsars are, in fact, among the most accurate clocks in the universe, rivaling atomic clocks in their precision over long timescales. But pulsars are also gradually slowing down. The emission of radiation and the interaction of the magnetic field with the surrounding space drain rotational energy from the star, causing it to spin slightly slower over time. This spin down is smooth and predictable, and by measuring it precisely, astronomers can deduce the strength of the magnetic field and the age of the pulsar. Except that sometimes, without warning, the spin down is interrupted. The pulsar abruptly speeds up. Not by a lot, mind you. The increase in rotation rate is typically a few parts per million, or even less. But because pulsar timing is so incredibly precise, these tiny jumps are unmistakable. They appear in the data as a sudden, discrete increase in spin frequency, followed by a gradual, partial recovery back toward the pre-glitch spin-down rate. These events are called glitches, and they were first observed in 1969, just 2 years after pulsars themselves were discovered. The Vela pulsar, a young, energetic pulsar located about 1,000 light-years from Earth in the constellation Vela, was the first pulsar observed to glitch. Since then, the Vela pulsar has become the archetype of glitching behavior, experiencing large glitches approximately once every 3 years with remarkable regularity. As of the early 2000s and 20s, more than 20 large glitches have been recorded from the Vela pulsar alone, along with a population of smaller, more subtle events. Roughly 5 to 6% of all known pulsars have been observed to glitch at least once. Some, like the Vela pulsar, glitch frequently and predictably. Others, like the Crab pulsar, glitch more randomly and with a wider range of sizes. Still others have never been observed to glitch at all. The leading theory for what causes glitches involves the superfluid interior of the neutron star. Remember that the core of a neutron star is a neutron superfluid, a frictionless liquid that can rotate indefinitely without slowing down. But the crust of the neutron star is solid, locked to the magnetic field, and it is this crust that is gradually being slowed by the emission of radiation. This creates a mismatch. The solid crust is slowing down. The superfluid interior is not. Over time, a velocity difference builds up between the two components. The angular momentum of the superfluid is stored in quantum vortices, tiny tornado-like structures that thread through the fluid. In a superfluid, rotation doesn't happen smoothly. It occurs through the creation of these discrete vortices, each carrying a quantum of angular momentum. Under normal conditions, these vortices are pinned to the crystalline lattice of the inner crust. They are stuck in place, unable to move. And so the superfluid co-rotates with the crust even as the crust slows down. But as the difference in rotation rate between the crust and the bulk superfluid increases, the forces on the pinned vortices grow. Eventually, the forces exceed the pinning strength, and the vortices unpin catastrophically. In an avalanche-like cascade, a huge number of vortices suddenly release their stored angular momentum to the crust, spinning it up in a sudden jolt. This is a glitch. A sudden transfer of angular momentum from the superfluid interior to the solid crust, manifested as an abrupt increase in the pulsar's rotation rate. The physics of this process is deeply connected to quantum mechanics. In a superfluid, angular momentum cannot be distributed smoothly the way it is in an ordinary liquid. Instead, it is carried by discrete quantum vortices, each one a thin tube of rotating fluid with a core only about a femtometer across, roughly the size of an atomic nucleus. The number of vortices is directly proportional to the rotation rate of the superfluid. A neutron star rotating at about 11 times per second like the Vela pulsar, would contain roughly 10 to the 19th vortices, or 10 billion of them, threaded through its superfluid core like invisible strings. These vortices interact with the crystalline lattice of the inner crust. At the lattice sites, the vortices experience a pinning force that holds them in place. As the crust slows down due to electromagnetic braking, the vortices should ideally migrate outward to reduce the angular momentum of the superfluid and keep it synchronized with the crust. But the pinning forces resist this migration. The superfluid maintains its original rotation rate, and the lag between the superfluid and the crust grows. Think of it like winding a spring. As the lag increases, the force on each pinned vortex increases. Eventually, the force exceeds the pinning strength, and a cascade begins. One vortex unpins, transfers its angular momentum to the crust, and the resulting disturbance causes neighboring vortices to unpin as well. The cascade propagates like an avalanche, unpinning millions or billions of vortices in a fraction of a second, and delivering a sudden kick of angular momentum to the crust. The size of a glitch depends on how many vortices participate in the avalanche. The Vela pulsar's large glitches involve a fractional change in spin frequency of about a few parts per million, which implies that roughly 1% of the superfluid's angular momentum is transferred to the crust in each event. Over decades of observation, astronomers have found that the cumulative effect of all of Vela's glitches accounts for nearly 1% of the star's total spin down, a remarkably clean number that places strong constraints on the fraction of the star's moment of inertia that is stored in the superfluid. In December of 2016, something extraordinary happened at the Mount Pleasant Radio Observatory in Tasmania. Jim Palfreman, an astronomer who had been patiently monitoring the Vela pulsar for nearly 4 years, received a text message alert from an automated system he had designed. The Vela pulsar had glitched, and for the first time ever, a radio telescope large enough to see individual pulses was watching when it happened. Palfreman had been collecting data at a rate of 640 megabytes every 10 seconds, 19 hours a day, for most days across nearly 4 years. The total dataset exceeded 3 petabytes, or 3 million gigabytes. When he logged in and examined the data around the glitch, what he found was utterly unexpected. At the exact moment of the glitch, the pulsar missed a beat. It nulled. For one rotation, no pulse was emitted. The pulse immediately before the null was broad and abnormal, unlike anything previously observed from Vela. The two pulses immediately after showed no linear polarization, which was also unprecedented for this pulsar. This meant that the glitch had somehow affected the magnetosphere itself, the region of magnetic field surrounding the star that is responsible for producing the radio emission. Following the null, a train of 21 pulses arrived early, with timing variations much smaller than normal. The glitch itself was estimated to have taken less than about 12 seconds to complete, and intriguingly, there was evidence that the pulsar had actually slowed down slightly in the moments immediately before the glitch, as if the crust had briefly decelerated just before the catastrophic transfer of angular momentum. This observation was a landmark. It opened a direct window into the physics of pulsar interiors, providing constraints on the properties of the superfluid, the strength of the pinning forces, and the coupling between the crust and the core. A later analysis of XDE J10-197, a magnetar that reawakened in late 2018 after a decade of silence, revealed that glitch-like events can also produce observable wobbles in the star's spin axis, caused by the surface becoming slightly lumpy, deviating from a perfect sphere by about a millimeter, before gradually smoothing back out over about 3 months. Glitches are not just curiosities, they are probes. Each one is a tiny window into the most exotic state of matter in the universe, a direct measurement of the behavior of superfluids under conditions that can never be recreated on Earth. They tell us about the equation of state of nuclear matter, the strength of the neutron star crust, and the dynamics of quantum vortices at densities that make the cores of atoms look positively spacious. Every glitch is a message from inside a dead star, encoded in the precise timing of radio pulses, waiting to be decoded. In April of 2025, a team of astrophysicists led by Anirudh Patel of Columbia University published a paper in the Astrophysical Journal Letters that added a stunning new chapter to the story of magnetar starquakes. They announced that they had found direct evidence that giant magnetar flares can forge heavy elements, including gold, platinum, and uranium. The discovery hinged on a 20-year-old mystery when SGR 18-6-20 unleashed its record-breaking giant flare on December 27, 2004. Multiple satellites detected the initial burst and the subsequent pulsating X-ray tail, but buried in the data from ESA's integral satellite, there was a second, weaker signal that peaked about 10 minutes after the initial flare. At the time, nobody could explain it. The signal was noted in the literature. And then, as Patel's collaborator Brian Metzger of Columbia University put it, largely forgotten. The explanation came from an understanding of a nuclear process called the R process, or rapid neutron capture process. This is the mechanism by which the universe creates elements heavier than iron. In the R process, atomic nuclei are bombarded by a torrent of free neutrons, absorbing them faster than the unstable resulting nuclei can decay. This rapid capture builds up progressively heavier and more neutron-rich nuclei, which then undergo a cascade of radioactive decays to produce stable heavy elements like gold, platinum, strontium, and uranium. For decades, the only confirmed site of R-process nucleosynthesis was the merger of two neutron stars. In August of 2017, the detection of gravitational waves from a binary neutron star collision, designated G170,817, was followed by observations of a glowing cloud of freshly synthesized heavy elements, a phenomenon called a kilonova. This was the first direct evidence that neutron star mergers produce heavy elements. The observation was a triumph for multi-messenger astronomy, combining gravitational wave data from LIGO and Virgo with electromagnetic observations from telescopes around the world. The kilonova's glow confirmed theoretical predictions that the merger would produce several Earth masses worth of heavy elements, including gold and platinum, scattered into space at a significant fraction of the speed of light. But there was a problem. Neutron star mergers are rare events, and they take a long time to happen. Two neutron stars in a binary system can take billions of years to spiral close enough to collide. The gravitational wave radiation that drives them together is extraordinarily weak, and the inspiral is correspondingly slow. This means that mergers couldn't have produced heavy elements in the early universe. When galaxies were still young and binary, neutron star systems hadn't had time to evolve. Yet heavy elements are observed in very old, metal-poor stars that formed within the first billion years of cosmic history, suggesting that something else must have been producing heavy elements early on. This timing problem has been called one of the major unsolved mysteries in nuclear astrophysics. Magnetar flares, Patel and his colleagues argued, could be something else. And the timing works perfectly. Magnetars form within tens of millions of years after the first massive stars appear, because they are born directly from supernovae. Unlike neutron star mergers, which require billions of years of binary evolution, magnetar flares can begin producing heavy elements almost immediately after the first stars die. This means they could have been active as early as a few 100 million years after the Big Bang, precisely when the unexplained early heavy elements appear in the fossil record of old stars. Their model describes what happens when a giant flare drives a shockwave into the magnetar's crust. The shock heats the crustal material to extreme temperatures and ejects a small amount of it into space at roughly 10% the speed of light. This ejected material is incredibly neutron-rich, a natural consequence of being ripped from the neutron-dominated crust of a neutron star. Under these conditions, the R process ignites, and heavy elements are forged in the expanding debris. As these newly minted radioactive nuclei decay, they emit gamma rays. And that, the team realized, is exactly what the mysterious 10-minute delayed signal from the 2004 flare looked like. When they compared their theoretical predictions with the actual data from Integral and other satellites, the match was remarkable. Metzger recalled that when Eric Burns of Louisiana State University first compared the prediction to the archival data, Burns thought the theorists were pulling his leg because the fit was so close. The team estimated that the 2004 flares produced roughly 1/1,000,000th of a solar mass in our process elements, equivalent to about a third of Earth's mass, or roughly 27 times the mass of the Moon, in heavy elements like gold and platinum. While this is small compared to the yield of a neutron star merger, magnetar flares are far more frequent. The researchers calculated that magnetar flares could be responsible for 1 to 10% of all the R process elements in the Milky Way, and crucially, magnetars form early. They are born in supernovae, which happen within tens of millions of years after the first massive stars form. This means that magnetar flares could have been producing heavy elements within the first few 100 million years of the universe's existence, long before neutron star mergers became common. The gold in your jewelry, the platinum in your catalytic converter, the uranium in nuclear reactors. Some fraction of these elements may have been forged in the cracking crust of a dead star, scattered across space by the magnetic fury of a starquake, and eventually incorporated into the gas cloud that collapsed to form our solar system 4.5 billion years ago. In 2007, the scientific journal Nature published a now famous editorial musing on one of the most tantalizing mysteries in modern astrophysics. Astronomers had detected a brief, intense pulse of radio waves that had originated from outside the Milky Way. It lasted just a few milliseconds, but was extraordinarily bright. Nothing in established astrophysics could readily explain it. The signal was designated by its discovery date and named a fast radio burst, or FRB. For over a decade, fast radio bursts were among the most baffling phenomena in astronomy. They arrived from all over the sky. Some appeared only once. Others repeated, firing off multiple bursts from the same location at irregular intervals. Their extreme brightness implied enormous energy, and their millisecond durations implied a compact source, something small, perhaps no larger than a city. About 50 different theories were proposed to explain them, a number that, for a time, actually exceeded the number of observed bursts. Ideas ranged from evaporating black holes to colliding neutron stars to the propulsion systems of alien spacecraft. Some theorists proposed that FRBs were caused by collapsing cosmic strings, one-dimensional defects in spacetime left over from the early universe. Others suggested they were the final cries of neutron stars collapsing into black holes. The difficulty was that fast radio bursts happened so quickly and from such unpredictable directions that it was nearly impossible to identify their host galaxies, let alone their specific sources. Without knowing where they came from, astronomers couldn't determine what was making them. It was like hearing distant thunder and trying to figure out what kind of storm produced it without ever seeing the sky. The first major breakthrough came in 2017, when the repeating fast radio burst FRB 100 and 21,000. 102 was localized to a small, star-forming dwarf galaxy about 3 billion light-years from Earth. This told astronomers that at least some FRBs came from environments associated with young, massive stars, exactly the kind of environment where magnetars would form. But it was still circumstantial evidence. Through it all, one class of object kept appearing near the top of the suspect list: magnetars. The reasoning was straightforward. Magnetars are compact. They store enormous amounts of magnetic energy, and they are known to release that energy in sudden, powerful bursts. If the radio emission mechanism could be identified, magnetars seemed like a natural fit. But the connection remained theoretical until April 28, 2020, when the smoking gun was found. On that morning, a newly built radio telescope in British Columbia called CHIME, the Canadian Hydrogen Intensity Mapping Experiment, was scanning the sky when it detected an extraordinarily bright burst of radio waves coming from within the Milky Way. The burst triggered 93 of the instrument's antennas, far more than a typical extragalactic fast radio burst. Almost simultaneously, the Star-Etwo radio array at Caltech detected the same signal. For a brief fraction of a second, the radio source was as bright as the sun. Christopher Bochenek, a graduate student at Caltech who helped lead the Star-Etwo project, later recalled the moment he realized what they had detected. The burst was thousands of times more energetic than anything previously seen from a source inside our galaxy. The source was quickly identified. SGR 1935 plus 2154, a known magnetar in our galaxy, roughly 30,000 light-years from Earth in the constellation Vulpecula. This magnetar had been intermittently active for years, producing occasional bursts of X-rays, but nothing like this. At the same time as the radio burst, multiple X-ray satellites, including ESA's Integral, the Agile satellite, and others, detected an X-ray burst from the same magnetar. The radio and X-ray emissions were coincident in time, confirming a direct physical link between the magnetar's magnetic activity and the production of the fast radio burst. The energy of this burst, designated FRB 200,428, was about 4,000 times greater than any radio pulse ever observed from a known galactic source. It was roughly 30 to 40 times less energetic than the weakest extragalactic fast radio burst observed to date, placing it in a regime that bridged the gap between known magnetar activity and the mysterious extragalactic signals. With a single observation, the mystery appeared to be largely solved. Magnetars could produce fast radio bursts. The mechanism was connected to the same magnetic energy release that powers starquakes and giant flares. Though the precise physics of how the radio emission is generated, whether through synchrotron masers in relativistic shockwaves or electromagnetic pulses launched directly from the magnetosphere, remains an active area of research. More recent theoretical work, published in 2025 by Bing Zhang and Rui Chang, who has explored whether all fast radio bursts, not just some of them, could have magnetar origins. They found that both isolated magnetars and magnetars in binary systems could explain the wide variety of observed FRB behaviors. Isolated magnetars, whose spin and magnetic axes become misaligned over time, might produce one-off or infrequent bursts. Magnetars in binary systems, where accretion from a stellar companion keeps the axes aligned, might produce the actively repeating bursts that have been observed from certain sources. If this picture is correct, then fast radio bursts are not just astrophysical curiosities. They are beacons, signals from magnetars scattered across the observable universe, potentially billions of light-years away. They could be used to build a census of magnetars far beyond our galaxy, to study the properties of the intergalactic medium through which the radio waves travel, and to probe the extreme physics of magnetic energy release in conditions that cannot be reproduced in any laboratory. Every millisecond, a flash from a distant galaxy might be the scream of a cracking magnetar, its agony broadcast across the cosmos. The implications are staggering. If magnetars are responsible for even a fraction of the fast radio bursts detected by CHIME and other observatories, then these bursts become tools of extraordinary power. Because fast radio bursts travel through the intergalactic medium, the ionized gas that fills the space between galaxies, their signals are dispersed in a frequency-dependent way. By measuring this dispersion, astronomers can calculate the total amount of ionized material along the line of sight, effectively weighing the intergalactic medium. This technique has already been used to locate the missing baryonic matter in the universe, the ordinary atoms that theoretical models predict should exist. But that had eluded detection in other observations. Fast radio bursts found them, hiding in the tenuous gas between galaxies. And if the magnetar connection holds, we may eventually be able to use fast radio bursts as cosmic probes, mapping the distribution of matter across the universe, measuring the expansion rate of the cosmos, and studying the environments of magnetars in galaxies billions of light years away, all from a signal that lasts a few thousandths of a second. We've talked about dead stars, about their interiors, their magnetic fields, their fractures and glitches and screams. But there's one more astonishing facet of this story that we haven't touched yet. One that is perhaps the most unexpected of all. Dead stars can have planets, not hypothetical planets, not theoretical possibilities, real, confirmed worlds orbiting the spinning corpses of exploded suns. Worlds that should not exist, that defy our intuitions about planetary formation, and that were discovered before any planet orbiting a living star was ever confirmed. The story begins in the early 1990s at the Arecibo Observatory in Puerto Rico. The enormous 305-meter radio telescope, nestled in a natural sinkhole in the karst hills of northwestern Puerto Rico, was undergoing maintenance. Structural defects had been discovered. Echoes of the recent collapse of the 300-foot telescope at Green Bank, and the decision was made to shut down normal operations for repairs. But the telescope could still be used in a limited way, pointed at a fixed position in the sky and used as a transit instrument, sweeping across the sky as the Earth rotated. Polish astronomer Aleksander Walskson, who had long been interested in searching for millisecond pulsars away from the galactic plane, seized the opportunity to conduct a survey. It was an act of scientific opportunism that would change the course of astronomy forever. On February 9, 1990, his survey turned up a new millisecond pulsar, designated PSR Bone 1257+12. It was spinning at an astonishing rate, completing 161 rotations per second, faster than the blades of a household blender. Located about 2,300 light-years from Earth in the constellation Virgo, the pulsar was unremarkable in most respects, just another spinning neutron star in a galaxy full of them. But when Walskson started making precise timing measurements, he noticed something peculiar. The pulses weren't arriving at perfectly regular intervals. There were tiny, systematic variations, deviations so small that they could only be detected with the exquisite precision of pulsar timing. The arrival times drifted forward and backward in a pattern that repeated over periods of roughly 66 and 98 days. There were only a few things that could cause such regular variations. An orbiting companion tugging the pulsar back and forth through its gravitational pull would change the distance between the pulsar and Earth by tiny amounts, causing the pulses to arrive slightly early or slightly late, depending on where the pulsar was in its orbit. Walskson carefully analyzed the data and concluded that the variations could only be explained by the presence of at least two orbiting bodies with masses comparable to Earth. The claim was extraordinary. Planets had never been confirmed outside our solar system. A few tentative detections had been reported, but none had survived scrutiny. And the idea that planets could exist around a dead star, a neutron star formed in a supernova explosion, seemed almost absurd. How could planets survive a supernova? Where would they come from? Wolskson was aware of the skepticism that would greet his findings. An earlier claim of a planet orbiting a different pulsar, PSR 1829-10, had been retracted when the variations turned out to be caused by a miscalculation of Earth's orbital motion. The embarrassment from that retraction hung over the field like a cloud. Wolskson had to be absolutely certain. Working with Dale Frail of the National Radio Astronomy Observatory, Wolskson published his findings on January 9, 1992, in the journal Nature. The paper announced the discovery of two planets, with masses of roughly 3.4 and 2.8 times the mass of Earth, orbiting the pulsar at distances of about 0.47 and 0.36 astronomical units, roughly similar to the orbital distances of Venus and Mercury from the Sun. These were the first confirmed planets ever discovered outside our solar system, not around a sun-like star, around a dead one. The reaction from the astronomical community was a mixture of astonishment and skepticism. An earlier claim of a planet around a different pulsar, PSR 1829-10, had been retracted due to calculation errors, and many astronomers were wary of a repeat. But Wolskson's data was solid, and subsequent observations confirmed the discovery. In 1994, a third planet was found in the system, with a mass of only about 2% that of Earth, roughly twice the mass of our Moon, making it the least massive exoplanet ever detected by any method. In 2015, an international naming contest organized by the International Astronomical Union gave these worlds and their host star proper names drawn from the mythology of the undead. The pulsar was named Lick, after a powerful undead creature from Western folklore. The three planets were named Draugr, Poltergeist, and Phobter, after, respectively, a Scandinavian zombie, a noisy ghost, and a Greek god of nightmares. NASA embraced the theme, releasing a series of Galaxy of Horrors posters depicting the planets as zombie worlds. The names are appropriate. These are worlds that exist in the aftermath of cosmic death. The star that originally created this system died in a supernova explosion billions of years ago, and any planets that orbited it during its lifetime were almost certainly destroyed in the blast. The planets we see today must have formed after the supernova, from debris left behind in the wreckage. They are, in every meaningful sense, the living dead of the planetary world, worlds that should not be, born from the destruction of the worlds that came before. The discovery of pulsar planets was so unexpected that the famous Polish astronomer Bohdan Paczynski compared it to the greatest discovery by a Polish astronomer since Copernicus. In 1998, Astronomy magazine included Wolskson's discovery among the 25 greatest astronomical findings of all time. And in a satisfying twist of fate, the confirmation of these pulsar planets came from the same property that made them so surprising. Because the two outer planets, Poltergeist and Phobter, have similar masses and orbit close together, near a 3:2 orbital resonance, they gravitationally perturb each other's orbits. These perturbations were detected in the timing data, providing independent confirmation that the planets were real and not some artifact of the pulsar itself. The timing technique used to find and confirm them was so precise that it could detect a planet with the mass of our moon, a sensitivity that no other method of exoplanet detection could match at the time. And that remains unmatched for objects of that size to this day. How exactly this happened remains a subject of active research. The leading hypothesis is that PSR Bone 1257 plus 12 formed not from a standard supernova, but from the merger of two white dwarfs. In this scenario, two white dwarfs in a binary system spiraled together and collided, their combined mass exceeding the threshold for neutron star formation. The collision produced a rapidly spinning neutron star, the millisecond pulsar, surrounded by a disk of debris from the disrupted white dwarfs. Over time, this disk coalesced into the planets we observe today, in a process analogous to the way planets form around newborn stars, but from entirely different raw materials and under entirely different conditions. If this picture is correct, then Draugr, Poltergeist, and Phobder are second-generation planets, born from the ashes of stars that had already completed their own life cycles. They are products of stellar recycling, assembled from the wreckage of not one but two dead stars. The planets of PSR Bone 1257 plus 12 are not the only zombie worlds known to science. Across the galaxy, a small but growing number of planets have been found orbiting pulsars and other stellar remnants, each one stranger than the last. Roughly 4,000 light-years from Earth, in the constellation Serpens Cauda, a millisecond pulsar called PSR J17 19-1000, 438 spins more than 10,000 times per minute. It was discovered in 2009 during a survey at Australia's Parkes Observatory, and subsequent timing measurements revealed a companion object in an extraordinarily tight orbit, completing one lap around the pulsar every 2 hours and 10 minutes. The entire system would fit inside the diameter of our Sun. The companion has a mass similar to Jupiter's, but a diameter only about 5 times that of Earth's, making it incredibly dense, roughly 23 times the density of water, or about twice the density of lead. Based on its mass, density, and the conditions of its formation, astronomers believe it is composed primarily of carbon, the crystallized remnant of a white dwarf star that was almost entirely consumed by the pulsar's gravity. Only about 0.1% of the original white dwarf's mass remains. And under the intense pressure acting on the planet's interior, that carbon is almost certainly crystallized. In other words, it's a diamond, a planet-sized diamond, orbiting a dead star at a distance closer than the Moon is to the Earth. The entire system would fit inside our Sun. The formation scenario is fascinating. Originally, PSR J17 19-1000, 438, and its companion were a binary star system. The more massive star died first, becoming a neutron star. Billions of years later, the less massive companion expanded into a red giant, and the neutron star's gravity began stripping away its outer layers, spinning the neutron star up to millisecond speeds in the process. This process of mass transfer is how millisecond pulsars are created. The material falls onto the neutron star, transfers angular momentum, and spins it up like a top being whipped by a string. Eventually, the companion shed so much mass that it shrank below the threshold for self-sustaining nuclear fusion and became a white dwarf. But even as a white dwarf, it continued to lose mass to the pulsar's relentless gravitational pull, until almost nothing was left except the dense, carbon-rich core. What once was a star became a planet, a world made of diamond, trapped forever in orbit around the creature that devoured it. This is not the kind of diamond you'd find in a jewelry store at 23 times the density of water, or roughly twice the density of lead. The crystalline carbon in this planet is compressed to a state that doesn't exist naturally on Earth. The crystal structure would be different from any terrestrial diamond, distorted by the immense pressure into a form with entirely different optical and physical properties, and the planet likely contains significant impurities of oxygen, nitrogen, and other elements left over from the white dwarf's nuclear burning history. It is, in the most generous interpretation, a diamond the size of a small planet, orbiting the corpse of a star that ate its sibling alive. Then there is Methuselah, a world that holds the title of the oldest known planet in the cosmos. Located about 5,600 light-years away in the globular star cluster Messier 4, Methuselah is a gas giant roughly 2.5 times the mass of Jupiter. It orbits a binary system consisting of a pulsar and a white dwarf, completing one orbit roughly every 100 years at a distance similar to Uranus's distance from the Sun. Methuselah is estimated to have formed approximately 12.7 billion years ago, within the first billion years of the universe's existence. To put that in perspective, the universe itself is about 13.8 billion years old. Methuselah formed when the cosmos was still in its infancy, when the first generation of stars was still lighting up the darkness. It has survived for almost the entire history of the universe, witnessing the formation and destruction of countless stars, the assembly of galaxies, and the slow evolution of the cosmos from a hot, chaotic fireball to the vast, structured universe we observe today. The existence of a planet this old raises fascinating questions about the early universe. When Methuselah formed, the universe contained far fewer heavy elements than it does today. The first generation of stars had barely begun to produce the carbon, oxygen, silicon, and iron that would later become the building blocks of rocky planets like Earth. Methuselah, as a gas giant, is composed primarily of hydrogen and helium, which were abundant from the very beginning. So its formation doesn't require heavy elements, but the fact that planet formation was already occurring within the first billion years of cosmic history tells us that the processes that build planetary systems were active almost immediately, not just around young, metal-rich stars like our Sun, but also around the very first stars in the universe. Scientists believe that Methuselah originally formed as a normal planet around a sun-like star within the dense stellar environment of the globular cluster. Over billions of years, gravitational interactions with other stars in the cluster led to the exchange of the planet from its original host to its current binary companion. Globular clusters are extraordinarily dense environments, with stars packed hundreds or thousands of times more tightly than in the solar neighborhood. In such crowded conditions, close encounters between stars are relatively common, and during these encounters, planets can be gravitationally captured or exchanged between systems. Methuselah has been orbiting the pulsar white dwarf pair ever since, a cosmic refugee from a solar system that no longer exists, the oldest known wanderer in the cosmic wilderness. And what would it be like in one of these zombie worlds? The conditions are, to put it mildly, inhospitable. Pulsar planets are bathed in intense radiation from their host stars. The pulsar's powerful magnetic field drives electric currents through the surrounding space. And if any of the planets have atmospheres, those atmospheres would be constantly lit up by powerful auroras, far brighter and more energetic than the northern lights on Earth. Imagine standing on the surface of Poltergeist and looking up. The sky would be ablaze with shimmering curtains of light, not the gentle greens and reds of terrestrial auroras, but harsh, energetic displays powered by relativistic particles streaming from the pulsar. And in the center of the sky, the lick itself would be visible, a tiny, incandescent point, spinning so fast that it completes one full rotation before you can blink, casting two brilliant beams of radiation outward into space, like a cosmic lighthouse gone mad. The surface temperatures depend on the planet's distance from the pulsar and the pulsar's residual heat. PSR Bone 1257 plus 12. The Lick pulsar has a surface temperature of roughly 29,000 degrees, far hotter than our sun's surface temperature of about 5,700 degrees. The innermost planet, Draugr, orbiting at just 0.19 astronomical units, is estimated to have a surface temperature only a few degrees below freezing. But this apparent mildness is deceptive. The radiation environment would be utterly lethal to any known form of life. Energetic particles streaming from the pulsar would strip away any protective atmosphere and sterilize the surface. Even if a thick atmosphere could somehow be maintained, the constant bombardment of X-rays and gamma rays would dissociate molecules and prevent the complex chemistry needed for biology. There is a deep irony here. The first planets ever found outside our solar system are among the least hospitable worlds imaginable. They orbit a dead star in a graveyard of stellar debris, bathed in lethal radiation, named after creatures from the mythology of death and horror. And yet their discovery was one of the most exciting moments in the history of astronomy, because it proved, for the first time, that planets are not unique to our solar system. Before Walskson and Frail's 1992 paper, the existence of extrasolar planets was a matter of speculation. After that, it was a matter of fact. The zombie worlds opened the door, and through that door poured a flood of discoveries: hot Jupiters, super-Earths, mini-Neptunes, circumbinary planets, and eventually potentially habitable worlds orbiting sun-like stars. As of 2025, more than 5,000 exoplanets have been confirmed, and the number continues to grow. But it all started with a dead star and its impossible planets. The largest survey of pulsar planets ever conducted, carried out by astronomers at the University of Manchester, searched more than 800 pulsars for planetary companions. They found that Earth-mass planets around pulsars are surprisingly rare, with only about 10 candidates identified. One promising system, PSR Jatwo 1007 plus 3120, located roughly 17,000 light-years from Earth, may host 2 planets with masses a few times that of Earth. The researchers also found that pulsar planets tend to have highly elliptical orbits, unlike the near-circular orbits of planets in our solar system, adding yet another layer of strangeness to these already bizarre worlds. These are not worlds where life, as we know it, could take hold. They are monuments to extremity, places where the ordinary rules of planetary science break down and something altogether stranger takes their place. Worlds born from death. Worlds orbiting the undead. We are living in a golden age of extreme astrophysics. The tools available to study magnetars, neutron stars, and their environments are more powerful than ever, and they are improving rapidly. NASA's Neutron Star Interior Composition Explorer, or NICER, has been operating on the International Space Station since 2017. By making precise measurements of X-ray emissions from neutron stars, NICER is mapping the relationship between the mass and radius of these objects, directly constraining the equation of state of nuclear matter. This is one of the most fundamental unsolved problems in physics. How does matter behave at densities far beyond what can be achieved in any laboratory? Every nuclear physics textbook has a chapter on the equation of state, and in every one, the section on supernuclear densities ends with an admission of uncertainty. NICER is helping to answer that question by measuring the sizes and masses of neutron stars with unprecedented accuracy. Its observations have already ruled out some proposed equations of state and narrowed the range of possibilities, bringing us closer to understanding what matter does at its most extreme. Astronomers are also hoping that NICER, or a future successor mission, will be operating when the next Magnetar starquake occurs. The last giant flare observed from a galactic magnetar was in 2004, over 20 years ago. Starquakes from galactic magnetars are estimated to occur perhaps once every decade or two, meaning that the next one could happen at any time. If it does, and if modern instruments are watching, the data could be transformative. High-time resolution X-ray observations of a starquake in progress would reveal the dynamics of the fracture, the properties of the fireball, and the behavior of the magnetic field in real time, providing a level of detail that was impossible with the instruments available in 2004. The discovery that magnetar flares can forge heavy elements has opened an entirely new frontier. NASA's upcoming Compton Spectrometer and Imager, or COSI, a wide-field gamma-ray telescope scheduled to launch in 2027, will be specifically designed to study energetic phenomena like magnetar giant flares. COSI will have the ability to identify individual elements created in these events by analyzing the specific energies of the gamma rays they emit. This will allow scientists to directly measure the composition of the material ejected by a starquake and confirm, element by element, what a magnetar can create. Gravitational wave detectors like LIGO and Virgo, which have already revolutionized our understanding of the universe through the detection of merging black holes and neutron stars, may soon be able to detect the gravitational waves produced by starquakes themselves. A sufficiently violent fracture of a magnetar's crust would deform the star slightly, creating ripples in space-time that could, in principle, be detected by the current or next generation of gravitational wave observatories. Detecting gravitational waves from a starquake would provide an entirely new way to study the interiors of neutron stars, complementing the information obtained from electromagnetic observations. And fast radio bursts continue to pour in. The CHIME telescope alone has detected thousands of these events since it began operations, and next-generation radio observatories, like the Square Kilometre Array, currently under construction in Australia and South Africa, will detect many more. Each fast radio burst is a potential probe of the magnetar population across the observable universe, a beacon from a cracking star that can be used to study the extreme physics of magnetic energy release, the properties of the intergalactic medium, and perhaps even the expansion rate of the universe itself. The story of magnetars, starquakes, glitches, and zombie worlds is far from over. In many ways, it is just beginning. Every new observation peels back another layer of complexity, revealing a universe that is stranger, more violent, and more beautiful than we ever imagined. Stars that die and leave behind magnetic corpses so powerful they warp the fabric of reality. Crusts that crack with the force of a trillion earthquakes, forging gold and platinum in the process. Superfluids that spin in quantum vortices and suddenly release their angular momentum in glitches that can be detected across thousands of light years. Planets that form from the wreckage of stellar death, orbiting in the hostile glow of an undead sun, are named after ghosts and zombies and gods of nightmares. There are still so many questions waiting to be answered. What is the equation of state of matter at the core of a neutron star? Do quark stars exist, objects even denser than neutron stars, where the neutrons themselves have dissolved into a sea of free quarks? What exactly triggers a magnetar giant flare? Is it the slow accumulation of magnetic stress followed by a sudden fracture, like an earthquake? Or is there a more complex interplay of magnetic reconnection and crustal dynamics? Why do some pulsars glitch frequently and predictably, while others never glitch at all? Are there more pulsar planetary systems waiting to be discovered? Or are they as rare as current surveys suggest? And perhaps the most tantalizing question of all, could there be planets orbiting black holes? If worlds can form from the debris of a supernova and survive in the hostile radiation environment of a pulsar, is it possible that similar processes could create planets in the accretion disks of black holes? A few theoretical studies have explored this idea, and while no such planets have been detected, the history of extreme astrophysics suggests that we should never underestimate the creativity of the cosmos. These are the extremes of nature. They are not anomalies or curiosities to be filed away and forgotten. They are laboratories, the only places in the universe where we can study matter at densities we cannot create, magnetic fields we cannot generate, and physical processes we cannot simulate. They push our theories to their limits, and frequently beyond. They show us that the universe is not governed by gentle processes and gradual changes, but by cataclysmic events of almost incomprehensible violence. Events that, paradoxically, are responsible for creating the very elements that make up our world and our bodies. Consider for a moment the chain of events that had to happen for you to be here, watching this, right now. A massive star had to live and die in a supernova. That supernova had to seed the interstellar medium with heavy elements forged in its core. Some of those heavy elements may have been produced by the cracking crust of a magnetar, scattered into space by a starquake. That enriched gas had to collapse into a new solar nebula, forming a star, our Sun, surrounded by a disk of debris that coalesced into planets, including Earth. The iron in your blood, the calcium in your bones, the gold in your ring. All of it was manufactured inside stars or in the violent events that accompanied their deaths. You are not just a passive observer of the cosmos. You are a product of it, assembled from materials that were processed through the most extreme conditions the universe has to offer. The gold in your ring was forged in the cracking of a dead star. The iron in your blood was built in the core of a dying sun. The neutrons in every atom of your body were once part of a gas cloud that was shaped, in part, by the energy released by magnetars and supernovae. You are, in the most literal sense, made of stardust and starquakes. And out there, right now, scattered across the Milky Way, magnetars are ticking. Their magnetic fields are slowly evolving, building stress in their crusts, inching toward the next fracture. Somewhere, a pulsar is about to glitch, its superfluid interior suddenly releasing a burst of angular momentum that will cause the star to spin up by a few parts per million. Somewhere else, a zombie world is silently orbiting its undead host, bathed in radiation, bearing witness to a universe that creates beauty from violence and order from catastrophe. And somewhere, a fast radio burst is crossing the void between galaxies, a millisecond-long scream from a cracking magnetar, traveling for billions of years before it reaches a telescope on a small rocky planet orbiting an unremarkable yellow star in the suburbs of the Milky Way. The universe does not owe us gentleness. It gives us extremes. And it is in those extremes, at the ragged edges of what is possible, that we find the deepest truths about the nature of reality. You've been watching. If this journey through the most extreme objects in the cosmos moved you, surprised you, or made you see the universe a little differently, hit that like button and subscribe to the channel. Leave a comment below and tell us which part of this story fascinated you the most. Was it the starquakes, the glitches, the zombie worlds, or the idea that the gold on your finger was born in the crust of a dead star? We'd love to hear from you. Thanks for watching, and we'll see you next time.